Forecasting with time series data. In this program, we'll review the moving average, simple exponential smoothing, the Holt method or double smoothing, as well as the regression methods for making forecasts from time series data. So here I am at the Forecasting Excel tool, and we'll begin by reviewing some of the basic patterns that we see in time series data. For example, if we look at this time series, which is the distribution of gasoline sales, and we can do that by adding our data simply to our time plot. We can see from the time plot that the pattern is horizontal, or what we call a stationary pattern. So we do see up and down variability, but that is mainly relative to a constant mean. Sometimes we see horizontal patterns that may appear to be upward looking trends. For example, the same gasoline data after acquiring a new contract could look very different. And so we do see a big jump up here at about the 12th month. However, the horizontal pattern continues. We just have a greater amount of sales, a new mean, in other words, because of the new contract, but the horizontal pattern continues. To look at a linear or an upward trend, let's clear these data and look at the time series bicycle sales. And we'll adjust our time plot. So now we do see an upward trend. It's not a horizontal pattern, but rather what we would say is a trend, and this trend happens to be upward. One more pattern that we see sometimes in time series data is what we call seasonality or seasonal variation. Like we see there. And we could adjust our plot to look at that whole time series. So just like with the bicycle sales, we see an upward trend, but we see a repeating variation which we call seasonality or simply seasonal variation. And these are smartphone sales. So what it shows is that throughout the course of a year, we see an increase in smartphone sales in a very predictable time of the year. Now, it's important to use our descriptive analytics, like we are here, visualizing the time series, to get a good idea of what the time series pattern is, because recognizing what that pattern is helps us to select the correct forecasting method. So now that we have some understanding of these basic patterns, either a horizontal or stationary pattern, or we might see trend, or we could see seasonality, and sometimes we see trend and seasonality together, we could look at the different forecasting methods and discuss which methods would be suitable for a particular time series pattern. So I'm going to look at the small business sales data, and I'm going to begin by studying the pattern using descriptive analytics. And we could see in this pattern a clear upward trend. Also, we might see a little bit of seasonal variation, but it's definitely not a clear seasonal pattern. So one method that we have for forecasting is called the moving average. And this is a very simple method because all we're doing is looking at a certain number of time periods and computing an arithmetic mean. For example, adding our sales data, the 2-period moving average simply averages the previous 2 time periods to produce a forecast. Now, the moving average method could be for 2 periods, 3, 4, or really any number. But remember, the greater the number of time periods, the greater the risk that our moving average would become imprecise. What we want is for the moving average to suppress noise or little bits of variation in our time series distribution by averaging out some of that. But we don't want so much of that to come out that we end up overestimating or underestimating with our moving average. For example, if I were to add our 2-period moving averages to the time plot, we could see that the moving average does suppress some of that noise. We see a smoother trend. However, the 2-period moving average is all below the actual sales data, which may lead us to conclude, and probably should, that the moving average here is underestimating the actual sales time series. Let's compare both of those now to the 4-period moving average. And we see the same thing. In fact, the 4-period moving average, although very similar to the 2-period, is maybe underestimating a little bit more. So the moving average is an appropriate method when we have mainly a horizontal pattern, possibly with some slight movement in the mean over time. The moving average would be suitable there. A main drawback, however, of the moving average is that it provides a constant weighting to each time period. Specifically, the earlier data is weighted equally as the later data in the process of creating our moving average. And this may not be a good idea because data that are farther back in history within our time series may be less representative of the present and the future. A good way to use averages, but to correct for what the moving average does, and namely, that is giving each time period equal weight, we could use simple exponential smoothing. And so I'm going to take the sales data and add it to the worksheet exponential smoothing. And the point of using exponential smoothing is that the method gives less weight to data that are in the more distant past, and then increasingly in an exponential or geometric pattern gives more weight to the more recent data. And this sounds like a pretty good idea. However, as we noted, our sales data has a clear upward trend. Generally, we would use exponential smoothing when the data do not have either trend or seasonality. We could see perhaps why by optimizing our alpha to minimize the forecasting error, or MSE. Alpha, our smoothing constant, ranges between 0 and 1. And what we would like is for our forecasting model to have a minimum amount of forecasting error. If we use our solver to optimize our exponential smoothing model, we could see the effect. Here we're going to set MSE to a minimum value by changing alpha, subject to the constraints that alpha, our smoothing constant, like any smoothing constant, stays between 0 and 1. Clicking Solve. Now we can see that in order to optimize this exponential smoothing model, we need to take our smoothing constant alpha all the way up to 1. The closer our smoothing constant is to 1, the less smoothing we achieve. In other words, our estimates would be rougher. When alpha is closer to 0, that's probably better because we're going to get more smoothing, and that's what we're trying to do with either the moving average or exponential smoothing method. So here we have optimized our exponential smoothing model, but the results are telling us that this method is probably not ideal for the sales time series data. And we expected that because the best practice use of exponential smoothing would be with a time series distribution that has neither trend nor seasonality, and of course does not have both. Now, in addition to simple exponential smoothing, and we call it simple, by the way, because we have only one smoothing constant, we could look at either double or even triple smoothing methods. And we're going to look at double smoothing, or what we call the Holt method. And we'll take our small business data, and we'll go to the worksheet Holt method, and add our time series. Now, Holt has an advantage over simple smoothing because it not only gives us a base level average, which is very similar to the moving average or the simple smoothing techniques, but Holt method also gives us a trend. And together, we use those two measures, our base level and our trend, to get our forecast or our predicted sales. Like any smoothing method, we have smoothing constants. And here we have 2 because we're working in our trend. But in order for these models to be effective, of course, we would want to optimize alpha. And we can see why. Well, now we have alpha at a very low value and beta at a very low value, and we see a very smooth result. Remember, closer to 0, more smoothing. And that's what we want, right? But we can also see that at 0.1 for alpha and beta, we have a considerable amount of forecasting error. In other words, we are deviating from the time series significantly, and we could see that on our visual. When we optimize, we could correct for some of that excess error. And we could use our solver to do this very efficiently. Again, our goal is to minimize or optimize the forecasting error. We're going to set that to a minimum by changing our smoothing constants alpha and beta. And both alpha and beta are subject to the constraints. Namely, they have to stay between 0 and 1. So our solver is set up, ready for us to click Solve. And once again, we have optimized the smoothing constants. But again, we see that alpha is all the way up to the maximum value of 1 in order to achieve that. So while we've reduced the forecasting error, we have not achieved much smoothing effect. This may lead us to believe that another method may be better for this particular time series. Now let's look at our final example, and here we're going to use linear regression as a forecasting model. And you can see that we've added in variable 1 the years 1 through 20, and in variable 3 those are our small business sales data. So we'll begin by running a simple linear regression with time as the independent variable and sales as our dependent variable. And let's look at the results. So the scatter plot shows us that this time series pattern fits a line very well. We don't have to optimize linear regression models in the same way that we would a smoothing constant, because the regression technique that we're using uses our least squares criterion. So the technique itself is trying to give us the line of best fit that minimizes forecast error. And we could see what the regression equation would predict for each year, and we could compare that to the actual sales data. For example, if we were to put year 1 into our equation, you could see that the forecast is 324.33. That's the number that we see here. The difference between the actual sales and the forecast sales is error. And we've previously termed this error a residual. Same thing. However, though we do see some errors, some differences, we can also see that the R-squared value for this model is about 92%. So this is a very good result and shows that perhaps a linear equation is a good way to reflect the pattern in this particular time series. And we did identify on our time plot, when we first looked at the pattern, we said that there was an upward trend. Now we could see that that upward trend is rather linear. So while the regression line seems to provide a very good fit with this time series, and we can see that also reflected in our R-squared, we clearly don't see a perfect fit. We might see also that the more distant past has a poorer fit than maybe from about the middle of the time series up to the present. That fits much better. So we might improve our model by using a quadratic adjustment. And to do that, we would use the year squared as an additional independent variable. And I've set this one up. We have two independent variables, 1 and 2. And of course, our dependent variable is still sales. So this would be a multiple regression. Looking at our results, we can see that both our r squared and our adjusted r squared, as we would expect, are increased a little bit compared with the results from our simple regression. Perhaps more importantly, we could also see that our MSE is reduced. And this is what we want, is to suppress some of that forecast error and get the best possible model. Now let's look at our time plot and compare the forecasts for both the simple regression and the quadratic multiple regression. So we've already mentioned where the forecast values are within the simple linear regression results, and those are highlighted here. For multiple regression, which is what we ran for our quadratic, they are on the worksheet residual 2. And we can take both of these forecasts, these sets, and add them to our time plot in order to compare them with the actual time series data. So let's do that. So here we are back at our time plot, and we could see that the orange series is just our original time series data for this small business. Now let's add a blue series that contains the forecasts made by our simple linear regression equation. So we can very simply copy and paste in order to compare. And of course, this is going to be a straight line because this was just simple linear regression. And the line fits fairly well. We could see that here we're lagging a bit, here over a bit. It's pretty good fit through this area of the time series distribution. But then we might overestimate a little bit coming up to the present. But as we said earlier, this is a very good fit. The reason we use the quadratic adjustment is to address curved patterns that aren't purely linear. So let's add the forecasts from our multiple regression or our quadratic. And we'll make that the red period. And we can see that these are very, very similar. As we would expect, we got very high r-squared values for both. So which is better? Well, perhaps we could say in terms of the r-squared value, the quadratic may be better. If we remove the simple regression forecasts, it would appear that it is a slightly better fit for the overall pattern. However, both models provide a very, very good fit. So in summary, we could see that it's very important when trying to create a model for forecasting with time series data that we first examine the time series pattern, because it's by understanding the pattern that we are able to select the best method to minimize forecast error and get the most accurate forecasts that we can. It's also worth noting that it is very possible that none of our standard methods may be appropriate for all time series or all businesses or all products. The needs for forecasting models vary widely, and it's important for us as analysts to understand these time series patterns, but also to understand our business need and at times be very innovative to adjust the way that we make our forecasts. This concludes the program Forecasting with Time Series Data.